Okay, this is podcast 5.4, and last podcast we talked about how you can predict the products of single replacement reactions. This time we're going to talk about how you can predict products of double replacement reactions. So, quick refresher, double replacement reactions are where you have two compounds and you kind of switch the outsides with the insides. There are rules that you need to follow, though, in order to know if a reaction is going to occur. You need to make sure that both the reactants are aqueous and at least one of your products has to be a solid or a liquid. If you don't meet both of those criteria, then you're not going to have a reaction. These reactions take a bit of time. They're kind of time consuming when you're trying to figure out if they're going to occur or not, because you have to use the laminated paper, you have to use the solubility table, and you have to look up each reactant to know whether it's soluble or not. And if it's soluble, that means it's aqueous, which is what we're looking for a lot of times. So kind of to get an idea of what happens with these, the double replacement reactions are often called precipitation reactions, and a precipitation reaction just means you're taking two liquids and producing a solid that wasn't there before. So in this example, the beaker that they're pouring into, so this solution right here, has potassium iodide in it, and potassium iodide is aqueous. When things are aqueous, what that really means is that they split into their ions. So aqueous potassium iodide really means I have potassium ions and I have iodide ions floating around. The same is true of the lead nitrate that they're pouring into, so this is the lead nitrate. The lead 2 nitrate, because it's aqueous, means I have lead ions floating around, and I also have nitrate ions floating around. So aqueous means it's able to dissolve. It really is in its ions. What you get, though, is when these two solutions mix, the lead and the iodine come together. So these green atoms from this solution and the purple atoms from this solution, when they join together, they form a solid, which is what you're seeing as this yellow solid right here. So the solid you will see come out of solution. And we did one of these on the demo day where we did all those different reactions, and it produced the white solid, if you remember the silver chloride. So precipitation reactions are just when we produce a solid that wasn't there before. Here is the table you need to make sure you have. Yours is yellow, mine is not, but this is the table that we're going to be looking at. So you can tell, for example, if I were looking up calcium carbonate, I would go, the positives are listed down the side, all the negatives are listed across the top. So the first part will always be down the side, the second part will always be across the top, and you just look for where they meet. So if I were looking for calcium carbonate, calcium is right here, and I just kind of work my way across the row until I hit carbonate. It tells me that it's a solid, that means it won't dissolve in water. Some other symbols, Ni means it doesn't exist, so if you're trying to produce that, it's not going to happen. Aqueous means it does dissolve in water. We have water, hydrogen and hydroxide would give you water. Oops. So you can read all the different types and symbols that are here, but this is a huge help when we're trying to figure out these double replacement reactions. Okay, the key to double replacement reactions is a lot of room. So I really recommend using scratch paper when you're trying to figure these out, and I'll show you why. I'll show you how I set them up to start with so that you can see how this works, but they do take up a lot of room. So I like scratch paper to do them. Here's what you usually get. I'm taking iron 3 chloride and mixing it with strontium hydroxide. First of all, I need to know, will this reaction occur, and then what will we get, and everything else. So the first thing I'm going to do to make sure I don't write formulas when I don't need to, because maybe this is a no reaction, is I'm going to check on my table. So if you check on your solubility table, you're going to look up iron 3 chloride. And when you look it up and find it, it's going to say it's aqueous. Then you're going to look up strontium hydroxide, and strontium hydroxide is also going to be aqueous on that solubility table. So far, both my reactants are aqueous. This is a good start. The next thing I have to check, though, is to make sure I get either one solid product or one liquid product. So when we're doing these, we remember that the outsides and the insides go together. So the iron 3 is going to go with the hydroxide, and the strontium is going to go with the chloride. And I connect them like this, and then I check them. So on the solubility table, I would look up iron 3 hydroxide. And what I'm going to find is that's a solid. And then if I look up strontium chloride, I'm going to find that that's aqueous. So now I've done everything, and I even sometimes go back through and put all the charges in here. Strontium is a +2, hydroxide is a -1. Now I have everything I need just to go in here and write this formula. It is really, really important that we include states of matter in this. So I'm going to have iron 3 chloride, aqueous. So remember, I'm starting with my reactants, plus strontium hydroxide, aqueous, gives me iron 3 hydroxide, solid, and strontium chloride, aqueous. So far so good. I wrote out the reactants, I wrote out the products. Now I have to balance 2 chlorines on this side, 3 on that side. I'm going to try and make 6. So 2, and then I'm going to put a 3 there. I need 3 strontiums and 2. Now I have 3 times 2 is 6 hydroxides, 2 times 3 is 6 hydroxides. Everything matches. So that's my final balanced equation. All right, the next one we have is silver nitrate. Silver nitrate and potassium chloride. If you can remember, all nitrates are always aqueous, and that kind of speeds the process up. Also, all potassium things are also aqueous. So for sure, both of those reactants are aqueous. My 2 products are going to be silver chloride, oh, excuse me, and potassium nitrate. Silver chloride, if I look that up on the table, is going to be a solid, and potassium nitrate is aqueous. So this reaction will happen. Both my reactants are aqueous, and I have one product that's a solid. So I'm going to quickly go through, and I'm just going to label charges here so that I can write it faster down below. I have silver nitrate, aqueous, plus potassium chloride, aqueous, gives me silver chloride, which was my solid, plus potassium nitrate, which was my aqueous. And before I even started writing, I knew I would be okay with balancing. I don't have to balance this because all my charges are identical. So this is it. We're good. I included states, and that's what you would do for that one. Next one, sodium nitrate. Sodium nitrate is aqueous, if you looked it up on the table, and potassium chloride is also aqueous. Sodium is going to go with the chlorine, and potassium will go with the nitrate. Sodium chloride, we should know, is aqueous, and then anything with potassium and nitrate is aqueous. So now, all of a sudden, all I have are aqueous things, and because there is no solid being formed, this is a no reaction. All I'm going to have is a bunch of ions floating around in solution, and nothing's going to happen. So that one is a no reaction, and we move on. The next one is copper 2 sulfate. Copper 2 sulfate is aqueous, and then sodium hydroxide is aqueous. In this one, the copper 2 is going to go with the hydroxide, and the sodium is going to go with the sulfate. So copper 2 hydroxide, when you look it up on the table, is a solid. Sodium sulfate is aqueous. So this reaction is good to go. I get a solid product. Copper 2 is a +2, sulfate is a -2, sodium is a +1, and hydroxide is a -1. So I'm going to go CuSO4, aqueous, plus NaOH, aqueous, gives me CuOH2, that was my solid, plus Na2SO4, and that's aqueous. So that's it written. I'm going to have to balance. I have 2 sodiums, 2 hydroxides, 2 hydroxides, and that's all I had to do to balance. All right, this one, sodium hydroxide, aqueous. Hydrochloric acid is aqueous. This one is a little tricky. If you can remember, hydrochloric is really HCl. I'm just going to write it out under there. So the sodium is going to go with the chlorine, and the hydroxide will go with the hydrogen. And sodium chloride we know is going to be aqueous, but hydrogen hydroxide, if you look that up, that's the same as water, so this is a liquid. Even though that's not a solid, this is a liquid, so two aqueous things are giving us a liquid. This is a reaction, we have to write it. This is one of the demos that we did together. So we have NaOH, aqueous, plus HCl. This is the one where we put the phenolphthalein in and watched it turn pink and then back to clear, and then it finally turned pink and stayed pink. So the other product besides NaCl was water. And this was a +1, -1, +1, -1. So since all the charges are either +1 or -1, I don't have to balance. Okay, this last one, I would recommend you try first. So pause it, you try it, and then see how you did when I go through it. Sodium chloride is aqueous. Calcium carbonate is a solid. So I'm hoping you didn't get very far when you tried this because you ran into a solid here, which tells you that this is automatically a no reaction because both your reactants have to be aqueous in order for this to work. So remember the rules when you're doing these, that you need to have two aqueous products or two aqueous reactants, and that has to give you one solid or one liquid. Make sure you're getting the right things, following the rules, and that you're remembering to cancel out charges first when you're writing formulas, and then to balance out the number of everything on both sides after you've written them correctly.